everyone. Welcome to the mind map of this electrostatics chapter. It will also include the capacitor part as well. So let's start with this chapter. In this chapter, the basic principle is the same, which is what we start with generally in electrostatics, is that there are two charges having charge Q1 and Q2. Then the force that is between them is equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. Now, this is the permittivity of free space. Q1 and Q2 are the charges on the respective charge particles, and R is the distance between them. Now, there's this another thing that we define here is the electric field or the electric field intensity, which is you can understand the electric field intensity in the term that let's say there's this charge Q, then how does it interact with the another charge? There's nothing in between them, right? It is free space. How is it that one charge is attracting or repelling the other charge? That is because of some sort of fields that it creates. You may consider it in the format of maybe Q is a spider here and it is creating a web around it so that another charge or analogous to a fly which comes in and interacts with the field or the web of the charge Q, then it gets stuck. Another charge Q2, if it enters the web field or the spider web of the charge Q1, then it will interact with Q itself, and the force uh, it will experience will actually be equal to this one. But this field Q should not depend on the second charge, right? Because the field is independent. It must remain as it is, as the spider's web remains as it is even in the absence of the fly. So that is why we define electric field in a way that it is independent of the other charges. So that is 1 by 4 pi epsilon naught q by r square, where r is the distance from the, or if we are talking about a point at which we want to find the electric field, then what is the distance from the charge itself? चार्ज से जितना डिस्टेंस होगा वो हमारा आर स्क्वायर बन जाएगा एंड क्यू हमारा चार्ज है जो इनिशियली उस चार्ज पे है. सो बेसिकली इलेक्ट्रिक फील्ड इज द inherent property of any charge. It doesn't depend on the second charge. All right. So this was electric field. But यहाँ पर let's say दो charges है Q1 and Q2. Now अगर Q2 fix कर दूं मैं and they are both positive, let's say, then, or maybe one negative, this one is negative, this one is positive, then हो क्या रहा है, मैं यहाँ पर इसको अगर छोड़ दूं तो after some point it will gain some acceleration, right? Because it is under the influence of the Coulombic force. This is Coulomb's law. And the Coulombic force will lead to some acceleration because the Q1 charge would also have some mass with it. So that will lead to some acceleration. And acceleration will lead to velocity. Where is that velocity coming from? There must be some source of energy, right? Because there was this charge, these two charges were static, placed at rest. When I leave the first charge, it gets attracted to the other one and gains velocity. अगर वो velocity gain कर रहा है तो कहाँ से उसके पास एनर्जी आ रहा है? बिकॉज वेलोसिटी के पास तो, और जब भी कोई ऑब्जेक्ट वेलोसिटी में होगा तो उसके पास तो काइनेटिक एनर्जी होगा ही होगा. तो काइनेटिक एनर्जी आ कहाँ से रहा है? दैट इज कमिंग फ्रॉम some sort of potential energy. What is potential energy? अगर आप ग्रेविटी में पढ़े होगे पोटेंशियल एनर्जी इज सिंपली एनर्जी ड्यू टू पोजिशन ऑफ अ बॉडी. इट इज अ स्टोर्ड पोटेंशियल एनर्जी. अगर उसको छोड़ दिया जाए या फिर उससे एक्सट्रैक्ट किया जाए तो अदर फॉर्म ऑफ काइनेटिक एनर्जी निकल सकता है, राइट. सो दिस इज पोटेंशियल एनर्जी. एंड हम क्या करेंगे अभी इस पे जो भी वर्क हो रहा है इस चार्ज के वजह से, उसी की वजह से उसका पोटेंशियल एनर्जी डिक्रीज हो रहा है, राइट. सो द पोटेंशियल एनर्जी कैन बी इक्वेटेड विद this thing F ds, बिकॉज वर्क जो भी कर रहा है सेकंड चार्ज फर्स्ट चार्ज पे, वही तो उसका पोटेंशियल एनर्जी गेन हो रहा है, राइट. सो एंड लेट्स रिप्लेस दिस वन, द होल थिंग 1/4πε0, उसको हम k बोलेंगे आपसे. दैट विल बी, or we will shorten up to call it as k because the whole thing is a constant. So k q1 q2 upon r square, the whole thing integral of dr. Now this comes out to be k q1 q2 upon integral of dr by r square. Integral of 1 by r square or r to the power minus 2 will be r to the power minus 2 by 1 by minus 2 plus 1. So that is simply minus 1 by or minus k q1 q2 upon r. This is the potential energy at any particular point which is r distance away from the charge. अभी हमने जैसे डिफाइन किया था, the way we defined electric field out of force, we can again define this is the potential energy, or U generally is the term with which we represent the potential energy. In a similar fashion, we can go towards a more independent form of energy field in which you can assume there is a charge and it is creating some sort of energy field around it, energy field which is called as potential. And whenever another charge q2 comes in contact with this potential, the potential energy in the system will be v into the charge q2. All right. So in a similar fashion, v is equal to minus k q upon r. All right. So these were the basic definition of potential and potential energy. I hope you know the difference now, because there is no external charge in the case of potential. Potential में हमने उसको ऐसा define ही किया है कि वो independent हो other charges से. Okay. So this was potential energy, and of course these are all for point charges, but there are other bodies, जैसे कि एक शीट है, इनफाइनाइट शीट, उसके लिए इलेक्ट्रिक फील्ड जब हम डिफाइन करते हैं तो वो आता है सिग्मा बाई 2 एप्सिलॉन नॉट, थिंग्स लाइक दैट. अभी अगर एक इलेक्ट्रिक और पॉजिटिवली चार्ज्ड स्फीयर है तो उसके अंदर का इलेक्ट्रिक फील्ड अगर r डिस्टेंस अवे हम निकाल रहे हैं अंदर का, तो इट विल बी E is equal to k q r upon r cube. पोटेंशियल इसका लिखते हैं k q upon r, yes, k q upon r, sorry, 3 minus small r square upon capital R square and this thing. This is the form of potential energy. So there are a few equations which you need to remember. I'll just mention it up because it is the out of scope of this particular mind map, but you should remember. For example, for line charge or linear charge. Second, for this thing, sheet. Third, this thing, ring, fourth disk, all these are charges. Fifth shell, and sixth sphere. Of course, it is spherical shell. Okay, so I hope you find them all and remember at least the electric field. If you are able to remember the potential as well, well and good. So that was electric potential. Now there is something called equipotential surface. All right. Now there's this point charge around which at r distance there may be maybe many points which are at r distance away. There can be n number of points which are in the shape of a sphere. All the points on the surface will have exactly the same potential. Why? Because the potential is equal to k minus kq upon r, where r is the same. अभी सभी तो r distance away है from the center or from the charge. So now सबका potential equal हो जाना चाहिए इस केस में. So it means basically if you move from this point to this point, there is no potential difference at all. That is why this whole surface will be called equipotential surface. एंड अगर इक्विपोटेंशियल सरफेस पे कहीं पे भी किसी पॉइंट पे जाना है तो देयर विल बी नो पोटेंशियल डिफरेंस एट ऑल. दैट इज द बेसिक थिंग टू टेक अवे फॉर दिस थिंग. नाउ electric potential due to charge, I think we have already covered it. Due to a system of charges, of course this potential is additive in nature. So अगर इस point charge q1 की वजह से इस point p पे अगर v1 पोटेंशियल है और इस पॉइंट चार्ज q2 की वजह से इस पॉइंट p पे v2 पोटेंशियल है, then the net potential at this point will be equal to v1 plus v2 because the potential is additive in nature. And of course potential is a scalar quantity. अगर हम वेक्टर क्वांटिटी की बात करें, लेट्स से अगर हम पॉइंट p पे इलेक्ट्रिक फील्ड की बात करें तो इलेक्ट्रिक फील्ड एट पॉइंट p ड्यू टू q1 should be in this direction e1 and with due to the point charge q2 should be in this direction if they are both positive. Then हम इसका सिंपल एडिशन नहीं करेंगे. अगर हमें ई नेट चाहिए so that will be e1 vector plus e2 vector addition of both of them. Okay, so it will come maybe something like this. So that was addition of or due to several charges. Now I think we can discuss about this one as well. So this is of course we have already discussed about it because it is simply kq upon r. If we took it from this point to this point, which is r2 distance away and r1 distance away from this charge maybe, then the potential difference can be written as potential at this one minus potential at this one. So potential at this one should be written in the format of kq upon 1 by r2 minus 1 by r1, right? So basically potential difference can be written in this format, v1 minus v2, but expressing v1 as kq upon r, kq can be taken as constant and taken out. So यहाँ पर ये होगा हमारा potential difference. If the separation between charge is r, then of course we have already dealt about it. ये भी हमने देख लिया है क्योंकि हमने देखा था ना कि this thing u is equal to v into q. So basically delta u change in energy is equal to q2 into delta v change in potential. So this is the same thing which I talked about just now. I think this is also clear. Now coming to a very important part which is called this thing, dipole. What do you understand by the term dipole? Dipole is basically two poles away, two poles which are away. For example, on the surface of Earth, we have two poles which are exactly diametrically opposite. So in the case of charges, a dipole is called, or a dipole is a system of two charges in which both of them are equal and opposite of each other. If this is plus q, then this is going to be minus q. Only then this it is going to be a dipole. And we connect it to be to with a maybe insulator so that the charges don't flow between each other. अभी इसको ये मान लो यहाँ पर का डिस्टेंस L है. Then we define a term called dipole moment, electric dipole moment. Dipole moment, which is denoted by term P, and it is actually equal to this charge on the body and L, the distance between the two opposite charges. This system is called dipole. This system is called dipole. And इस dipole के लिए dipole moment हम define करते हैं. And if you actually talk in terms of this thing, then it will be from the negative charge to the positive charge. Of course, it is a vector quantity. So the direction will be from the negative charge to the positive charge, whatever direction it is. Okay. So this is about dipole moment. But dipole moment के लिए हम क्या करते हैं? Field हम define करते हैं. For example, let's say this thing. This is minus q and this is q. When you talk about any point which is on the line of the dipole, let's say this is at the line of the dipole P. अभी उसका distance कैसे find करेंगे dipole से? There are two different charges. Then we actually, whenever we find a distance with respect to the dipole, we take the middle point as the reference point of the dipole. So this is the r distance, and in that case, case 1 could be on line of dipole, जैसा हमने अभी ये बनाया इसमें, इस केस में. तो on the line of dipole, the electric field is given as, we'll also find potential. So electric field is given as 2p, sorry, k 2p upon r cube, and the potential is given as, sorry, k p upon r square. This is on the line of dipole. You must remember it. This is k. K is the same 1 by 4 pi epsilon naught. But if you want to find out, let's say at the bisector, मतलब उन दोनों charges के बीच में, this is a charge and this is another charge, then on this bisector, if you take any point, let's say P2 point, which is r distance away, then इसके लिए on bisector of the dipole, मतलब कि जो point अगर हम shortest distance find करेंगे from the dipole line, it will actually bisect the line. So that is called bisector. It could be in either direction, let's say in this direction as well, or maybe coming out of the board as well. So in that case, electric field is written as minus kp upon r cube, and the potential is actually equal to 0 in that case. So ये चार result हमें याद रखने हैं, so that questions on dipole could be solved very quickly. Now there is another result on dipole that you must remember, which is about the torque. This is what we dealt with now. Let's say this is the dipole, q and minus q, and joined by some line, a straight line. Now if there is an electric field, a continuous electric field, what is this charge going to experience? A force in this direction. What is this charge going to experience? A force in the opposite direction, because it is having a negative charge. Now these two forces are equal in nature, of course, and they will add up to zero, no problem. But there is this going to be a situation like a pole on which this force is acting on this direction and this force is acting on that direction. It will something look like this thing when I'm pulling it from this direction and pulling the other end with this direction, so it will start to rotate, right? So it will experience a torque here, and the torque could be given as P cross E. These are vector product, and of course initially it was having no energy, while after some time it will rotate, due to which it will gain some angular velocity, and the kinetic energy could be given as I omega square, right? I omega square. If it has some omega, then it will have some kinetic energy. Where is that kinetic energy coming from? वो kinetic energy कहीं से तो आएगा नहीं, इसके अंदर होगा potential energy. So potential energy of a dipole is simply written as P dot E minus P dot E. Of course, P and E both are these vector quantities, so we'll treat them accordingly. उसका क्रॉस प्रोडक्ट हमें देगा ये टॉर्क, which is this one, and dot product will give me this thing, potential energy. Now I think we have more or less talked about all these. Electric potential due to, yes, work done. Actually we have talked about work done also, because we were defining the potential energy there. Then we had talked about work done as well. Now coming to the second part of this chapter, which is about capacitors. Maybe we can take it here. Now let's say we have a shell, and we provide some electric field into it, or maybe connect it to a wire and connect it to some potential difference of V. What is going to happen? First of all, whenever we apply some potential, the charge, some of the charge will accumulate on the surface, which will be actually equal to, let's find the potential on the surface of shell. Of course, this is a shell. The potential on the surface of the shell is equal to K Q upon R, right? Minus K Q upon R. For the this magnitude sake, let's take it up here, K Q upon R. Now, after applying some potential, what we are left with is some charge. What is happening over here is, हमने कोई ऐसा मशीन फाइंड किया जिसमें अगर हम पोटेंशियल डिफरेंस लगा दें या फिर इलेक्ट्रिसिटी से कनेक्ट कर दें, दैट इज बेसिकली पोटेंशियल डिफरेंस, तो उसमें कुछ चार्ज रह जाएगा, दिस चार्ज. So basically, did we find out a machine which can store charge for us? Of course. So what we define here is capacity. What is this capacity? Capacity to store charge is called capacitance. अब ये capacitance है क्या? मतलब कि अगर हम बेसिकली क्या है, वी आर अपॉन के इज इक्वल टू क्यू. सो बेसिकली अगर हम पोटेंशियल डिफरेंस जो भी लगा रहे हैं इसके बीच, अगर हम वो बढ़ाते जाएं तो चार्ज भी बढ़ते जाएगा. सो बेसिकली charge is directly proportional to voltage which is provided to the system. अगर हम इसको proportionality को equality में convert करें, Q becomes some constant C into V, where C is actually called the capacitance of the system. Capacitance basically, अगर हम इसको voltage V provide कर रहे हैं तो उसमें कितना charge store हो रहा है, that is basically capacitance. Q by V is equal to capacitance. Charge stored per unit voltage. So that's the definition of capacitance. कि बेसिकली उसका काम है कि हमें चार्ज स्टोर करना है, अब उसके लिए कितना वोल्टेज लगाना पड़ेगा बताओ जल्दी. Just a second. Yes. So that is the capacitance of the system. Now we will talk about the energy stored in the capacitor. The energy stored will be actually, how will you define the energy stored? Actually, that is a slightly lengthy, so I'll just give you the formula because I will have to use parallel plate capacitor and electric field around it. Electric field can be given in the format of, see, these are parallel plate capacitors. Generally, we use, this is not a general capacitor because when we try to find out the estimates of the size of this one for uh, storing certain charges, it turns out to be very big. So physically not possible to use it in electronic machines. That is why we devised something called parallel plate capacitors. Basically, two very thin plates are placed parallel to each other in almost very close proximity, and capacitors for that thing is actually equal to A epsilon naught by D. This is the capacitance of the parallel plate capacitor, in which it depends on the area A, surface area, whatever surface area is this one, and it is inversely proportional to the distance between them. So basically आप जितना close लाते जाओ उस कैपेसिटर का कैपेसिटेंस बढ़ते जाएगा. It can store even more high amounts of charges. Of course, after a certain minimum amount of width between them, the circuit will actually fuse and basically एक दूसरे से connect हो जाएंगे वो. So except that case, it can store high amount of charges until the breakdown point. So this was about the parallel plate capacitor, and the energy stored in capacitors is actually equal to energy stored in the capacitor. Of course, energy is being stored, right? Because it is basically two different plates which are storing, one of them is storing positive charge Q, where another one is storing negative charge Q. अभी दो अलग अलग चार्जेस को सेपरेट करने में एनर्जी तो जाएगा. So basically that energy is stored in the format of this capacitor, and that is equal to half C V square, or even given in the format of half Q square upon C. This is more easier to remember, so it is very straightforward. So this was the energy stored in the capacitor. Now there is something called, yes, I think we should first define dielectrics. Now let us say these are the two plates in which, what is this inside? It is vacuum. And what's the permittivity of vacuum? Epsilon naught. Let's say I have another material which I insert into it. Now the property of this material is such that it has a different permittivity. Permittivity is basically the property of any medium to allow electric field to pass through it. Of course, the vacuum is going to be have the uh, most permeability, or the highest amount of property to let the electric field pass through it. But there could be another materials in which they will be slightly restricting towards the electric field. It will not allow all of the electric field to pass through it. That type of materials are called dielectrics. Now, the dielectrics will have a different epsilon. It is not going to be equal to epsilon naught. So the epsilon that they have, we generally uh, generally do not take into account the epsilon dash because it will create confusion. So what we do is define a constant which is called dielectric constant. It is the ratio between the permittivity of the material with respect to the permittivity of free space. This is the dielectric constant given by the term K. मतलब कि अगर हम कोई और प्लेट के बीच में अगर पहले वैक्यूम था, उसके बीच में हम कोई और सब्सटेंस डाल दिए हैं, तो ऑफ कोर्स उसका प्रॉपर्टी स्लाइटली डिफरेंट होगा. वैक्यूम जितना इलेक्ट्रिक फील्ड को पास होने दे रहा था, तो डाइलेक्ट्रिक उतना पास नहीं होने देगा. इस वजह से हमारे पास थोड़ा सा हिंड्रेंस आएगा, और इस प्रॉपर्टी को हम डाइलेक्ट्रिक कांस्टेंट के टर्म में रिप्रेजेंट करते हैं, विच इज द रेशियो ऑफ द डाइलेक्ट्रिक कांस्टेंट ऑफ द मटेरियल, sorry, permittivity of the material with respect to the permittivity of free space. This is the K that you have to remember. Now, due to, let's say there is this capacitor which has been charged with some wire, so plus Q and minus Q are there. Now what I do is insert a dielectric constant or dielectric with a dielectric constant of K. Now suddenly, after inserting the dielectric constant, the electric field will reduce E naught by K. The potential difference will also reduce. But the charge is not going to reduce. Why? Because dielectric is not a conductor. It is not going to conduct your charges. So whatever charge initially the body has or one of the plates had, it is going to retain it. The charges are not flowing in any direction. It's just the matter of electric field which is changing. So this was dielectric constant. Yes, of course, it's you just have to replace epsilon with the epsilon naught, epsilon with epsilon dash, or replace epsilon with the k epsilon naught. It is just the same thing. It is equal as per the definition of dielectric constant. So that is the dielectric and capacitance of the parallel plate capacitor. Of course, the capacitance of the parallel plate capacitor was A epsilon by sorry D. अब यहाँ पर epsilon ही change हो गया है, तो it will become epsilon naught C dash, sorry, epsilon dash, where epsilon dash is equal to k into epsilon naught. So it is basically C dash is equal to k into C original. So capacitance भी बढ़ जाएगा k times. It's just that the charge will not change. Capacitance will increase by k. The field and the potential will decrease by k, a factor of k. So this is also covered. Now coming to a very specific situation in which let me explain it here. Let's say I have a parallel plate capacitor having distance d between them. Maybe I should use another color for you to distinguish. Having color d, or sorry, the distance bit d between them, area is A, and what I do here is introduce a dielectric which is partial, just partial width. It is not the whole width which is being covered, or x. It is just the partial width of the capacitor which is being covered by the dielectric. Rest is still vacuum. So in this case, the capacitance will look like something like k epsilon A divided by k d minus x k minus 1. This can be derived using electric field, क्योंकि यहाँ पर electric field जो change होगा, we already know electric field is equal to electric field E naught by K, and it will remain the same here. So the whole potential difference can be calculated easily, and it is basically the charge with respect to potential difference, which is the ratio of the capacitance. So using that method, you can derive it, but we do not have the time for deriving all that. So we'll just remember this formula for the changed capacitance of the system when partial dielectric is inserted into the capacitor. Now this spherical capacitor, I think we already discussed. What was that? In this case, this was, let's say, this capacitor, this spherical shell. If you want to find out the capacitance of this one, you will have to do Q upon V, right? Let's do that. Q upon V. What is the potential for such shells? KQ upon R. So Q gets cancelled out and you're left with R upon K. So basically R upon 1 by 4 pi epsilon naught. So capacitance for this spherical shell comes out to be 4 pi epsilon naught R. And let's say you have two different shells of radius R1 and R2, R1 and R2. Then in that case, it will look something like this, the capacitance. Spherical capacitor. For isolated sphere, we already talked about this one. And for spherical capacitor, it will look something like this. 1 by R1 minus 1 by R2. Let's say we have two different shells. Then the capacitance of the system, when you join this one, A point and B point with the voltage, then the capacitance of the system will be actually 4 pi epsilon 1 by R1 minus 1 by R2. R1, R2. Okay. These two you should remember because it's important. Many times straightforward is asked. Now, it's just one part which is left, except this one. I think it is more suited for the chapter of current electricity, conductors and insulators. That is why we'll discuss it in that mind map. This only one part in which capacitors are generally represented by this sign and introduced in circuits as well. Let's say this is the circuit, something like this. So in this case, this is a single capacitor, so everything is simple for this one. But let's say I have two capacitors which are joined in series. Of course, you remember this one from your earlier classes in करंट इलेक्ट्रिसिटी कि हम सर्किट में अलग अलग रेजिस्टर्स वगैरह सीरीज में क्या पैरेलल में ये सब लगा देते थे. तो देयर कुड बी टू डिफरेंट केसेस. दिस इज अ सीरीज वन and maybe this could be another situation in which the two AB and AB, between point A and B there could be two different combinations of capacitors parallel. There could be two different combination of capacitor combining the capacitor. One could be series and another could be parallel. अभी हमारा resistor में क्या होता था, अगर series में होता तो simply add up हो जाता था, R is equal to R1 plus R2, and parallel में होता था 1 by R net is equal to 1 by R1 plus 1 by R2. But here it is entirely opposite, that you have to remember, that in series 1 by C net is equal to 1 by C1 plus 1 by C2. In the parallel, it is simply C net is equal to C1 plus C2. Of course, if you have multiple uh, plate capacitors in series, एक है, दो है, तीन है, further that, then in this case it will be 1 by C net is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. And in case of parallel plate capacitor, you will have a case like C net is equal to C1 plus C2 plus C3 plus so on. So you can combine even more capacitors, not a problem. So in that way, we can calculate the capacitance of net capacitance of different combination of capacitors. So I think we have dealt with rest of the points as well. This we'll talk about in the chapter of current electricity because it is more apt for that. So that is all for this mind map. I hope this was helpful. Thank you.